Today, I have discussed about the enthalpy changes in different physical process. Today, we are going to discuss enthalpy changes in some chemical process. So, suppose we carry out a reaction. Reaction always any chemical conversion, or as you have seen in case of physical conversions, the energy is involved. In a chemical reaction, also energy is involved. So, in such case, that we are going to discuss. So, let us go for now enthalpy change in chemical reaction. Change. Chemical reaction. The enthalpy change accompanying the chemical reaction is called enthalpy of reaction. It is denoted by delta R H. Okay. Okay. I do to change, yeah. Under standard state. Standard state, 1 bar pressure at 298 degrees Celsius is called standard enthalpy of reaction. It is denoted by delta R. Now, we know that enthalpy is a state function. What is that state function? That we cannot find out how much amount of the energy is involved in every step. But we can find the difference between them. What was the enthalpy at the beginning of the process, and what is the enthalpy at the end of the process? And if you subtract that one, we can find out the enthalpy change. Now, in a chemical reaction, in a physical process, we have mentioned initial state and final state. In a chemical reaction, what is the initial state? Initial state is the reactants. And what is the final state? Is the product. Okay. So therefore, what I can write here now? Therefore, delta AI0 is sum of the, I'll put this is summation, sum of the enthalpies of products, that is the final, minus sum of the enthalpies of reactants. That way we can calculate. So therefore I can write now in this symbol we will put. Now here we will not.
Sir, done.
Now we write here. Second is enthalpy of formation. Is same as that of reaction only. Enthalpy of formation. Okay. The enthalpy change when 1 mole of a substance is formed from its elements. From its elements in the most stable form. Is called enthalpy of formation. Okay. It is denoted by delta H is 0, sorry, delta F is 0. Every time I forget. Formed from its elements in their stable forms, please write here. Under standard state. So here what we will write now? Delta F, the sum of the standard enthalpies Some of the standard enthalpies of formation of products and some of the standard enthalpies of formation of reactants. So I'll write down here delta F is the now I'll not do the numericals. We'll do later on. Don't worry, I'll do the numericals for you. The numericals of thermodynamics are not difficult, but only thing is that these numerals are little bigger. So in that case, if you do it once or twice, then you'll find your confusion will be removed. Now we'll go for bond dissociation enthalpy. The energy to break 1 mole of bond of a particular between
makes sense. It's easy
two
to
atoms
because there are customer के लिए delivery delivery time कम हो जाएगा ना
in the
पास में उतना जल्दी तेरे को चीज
initial
ये
state
बहुत ये
is called bond dissociation enthalpy. Is denoted by C small a.
So what is before H?
Huh? What you
What
saying?
is before H?
A small
Or
a.
what is before that?
Delta A.
Okay,
A is
sir.
the subscript. Okay. Huh?
बहुत कौन student है
Just excuse me, your student. See, this bond I have to break. Okay. So here in this case, the energy is delta H0 energy is 435 kilojoule. Okay, but I'm supposed to find for one atom. After breaking, how many atoms I get? Huh? See here, when I break it, I get here 2 atoms. But I have to find for, see here, what does it say? 1 mole. So in that case, here I write now delta H0 is 435 divided by 2. So it is 275.3 kilojoule mole inverse. All right, understood? Just a minute.
Sir, done.
So now this is the bond enthalpy. Now see here, there are some molecules where you find that more than one bond is there. So in that case, what should I do? See here you have only one bond. Here we have 4 bonds. So in this case, what you do? For each breaking of bond, you will get a value. This is the one which you should try to understand. See here. So I have taken this. When I hit, it will break. To give you what? It will break to give you this. One bond is broken. So I'll write now here A1H. Okay. So it is equal to 427. You need not write, you get in your book also. 0 kilojoule mole inverse. Then, see, very interesting. Then, again you break. Then you will get here now CH plus H. So here I'll write now delta A to H. So it is 439 kilojoule mole inverse. So again you hit all of them, they break stepwise. And when carbon and hydrogen combine, they also combine. First one bond will form, then second bond will form, third, then fourth. So I'll write here now this. So it is 452 kilojoule mole inverse. Then the last bond is going to break. Okay, so we'll get now carbon and hydrogen. So I'll write now here A4H is equal to 347.0. So in that case, what you do? We add all of them. So here I'll write. Therefore, this is equal to delta A1 H0, delta A2 H0, delta A3 H0, delta A4 H0 divided by 4. So it comes to 416.25 kilojoule mole inverse. Okay, so this is called average bond dissociation enthalpy, or you call bond enthalpy. So when they call bond dissociation enthalpy, please remember we are breaking a bond between two similar atoms, like breaking of hydrogen bond, bond between two oxygen atom, bond between two nitrogen atom, bond between two fluorine atom, bond between two chlorine atom, because these molecules are being formed by the same atoms. Or you have only one bond between two atoms. I should not say one bond, one type of bond. It may be single bond, double bond, or triple bond. But if you have multiple bonds, in that case, whatever the energy that you calculate, it is nothing but the average energy of all the bonds broken in successively. So please try to understand there's a difference between bond enthalpy and bond dissociation enthalpy. Bond enthalpy is nothing but the average of the bond dissociation enthalpy. Clear? Okay. See, whenever you carry out a chemical reaction, you take reactants, you break the bond between the reactants, and after that again you form a new bond. So chemical reaction is nothing but breaking of bond and the formation of new bond. All right. So now, in that case, I can write the enthalpy of reaction, that is, you can write here delta R H0. Can we calculate it from bond enthalpy of the reactants and products. So initially, enthalpy of reaction, how did you calculate? Enthalpy of reaction we have calculated from the enthalpy of the formation of products minus enthalpy of formation of reactants. Again, here you can calculate in other methods. It is RH0 is equal to sum of bond dissociation enthalpies. See, all the cases we have put products first minus reactant, but when you take bond dissociation enthalpy, you first take reactant. Enthalpies of reactants minus sum of bond dissociation enthalpies of products. Okay, so I can write therefore delta R H0 delta A H0 reactants তাই শব্দ বানাবি products. We'll do some numerical later on. একটু গরম করে দিলাম আমি গরম করে দিই wait a minute. Áp phẳng mo. ये ढूंढते भी नहीं मिलता. One sum will do from bond enthalpy. Very simple sum. Calculate the enthalpy of reaction delta R H0. What is the reaction? Say you have taken chloromethane and you have broken down. You have decomposed it. Two hydrogen and two chlorine. Bond energies of CH.
Happy birthday. Happy birthday, video.
CCl. Bond R 415 kilojoule and 325 kilojoule respectively. Okay. So now, what is the answer now? You know it. Answer is what? Delta RH is equal to delta H0 reactants. Sorry.
No.
Minus delta A H0 products. See here. Please see the right hand side. They are all atoms. There is no bond. So it is 0. So you have get here. Now see how many carbon-hydrogen bonds are there? 2. So you have to multiply it by 2. How many carbon-chlorine bonds are there? 2. So you multiply this one, you get the result. Put, do. It's only a matter of 1 minute.
You are also moving with the umbrella, Papa.
So 180, sir.
How come it is 1482 kilojoule? Hey, how come it's 180? See here, in this case is what? How many bond you have here? 2H. So it will be what? 2 into 450, 50. Okay, plus 2 chlorine. So 2 into 325, and this is 0 because they are all in atomic states. So add. Thermochemical reaction. See, any chemical reaction, it involves heat. Either it releases it, which you call it exothermic reaction, or it absorbs it, which you call them as endothermic reactions. Okay, so I'll write here the definition of thermochemical equations. When a balanced chemical equation not only indicates the quantities of different different reactants and products but also the amount of involved. That's involved. I think that evolved or absorbed in the reaction is known as
I found relation was good. That's the
Thermochemical.
maybe not.
Okay, so I'll give you two examples.
I was telling it's not much to do not bother.
N2G plus 3H2G. It gives you ammonia and it releases heat. Okay, so here you find delta RH is equal to 92.4 kilojoule mole invert. So when you write this one complete, then we call it thermochemical reaction. Others looking at this, you do not know whether it absorbs it or it releases. Okay, so now if you decompose this one, what will going to happen? You will just, this will come to the right hand side, and you will find in that case you have to hit to break it, decomposition. So it will be delta R H0 is equal to 92.4 kilojoule. So now you know this is endothermic, that is you have to heat, and this is exothermic, which gives out heat. Bye. Okay. Now we'll go for there is a term called Hesse's Law. Law of constant heat summation. See, all the law I need not write, I'm telling you. See, a compound can form in one step, or a compound can form in more than one step. So, if the compound which is being formed in more than one step, in each and every step heat is involved. If you add them together, it will be same if the same compound is formed in one step. So that is called Hesse's law of constant heat summation. Okay. Wait. I'm reading, why did I write it? Why did I write? Change in a chemical reaction is the same whether the reaction takes place in one step or in several steps. Okay. So I'll give you one example. See, carbon to carbon dioxide. So in case 1, where you find that carbon get, in one step, carbon get converted into carbon dioxide. So I'll write now here, carbon dioxide. This is an exothermic process because if you burn coal or carbon, it produces heat. So in this case, enthalpy of reaction is equal to minus 394.0 kilojoule mole inverse. And in case 2, it may occur in 2 steps. Carbon with a limited supply of oxygen, first it will give you carbon monoxide. And it happens. You'll find during winter in Shillong earlier time, because people used to use coal for warming the house, and they close all the door and window. Many times you find people die because of carbon monoxide. So here, enthalpy of reaction is minus 110.5 kilojoule mole inverse. And this carbon monoxide can again burn. That you have seen carbon monoxide, when it burns, it gives you blue flame. This. So I'll write now here, H0 is minus 200 kilojoule mole inverse. দাম 1400 না? So now if I add it, you'll find it is 394.5 So if you do in one step, or if you do in multiple steps, this is safe. Yes, tell me.
Sir, should it be minus 394?
Yes, that you know, dear. This printing mistake. Now we'll go for lattice enthalpy. What is the meaning of lattice enthalpy? See here. You have seen in your house you are using atta or maida. They do not have any specific shape. We call them, they are in the powder form. But if you look at the sugar and the salt, you find they have a specific shape. Okay? We call them as crystal. All right. This specific geometry by which the sugar molecules or the salt, sodium ion and chloride ions are arranged, this is called lattice. Okay, so lattice is the boundary. Within that, them thousands and thousands molecules they remain. So they have come together, they got systematically arranged and formed a definite geometric shape. If you break this wall, all the molecules will be set free, will go out. So the amount of energy that you require to break 1 mole of crystal, that is known as lattice enthalpy. Okay. Amount of energy means what? Enthalpy only. Required to break 1 mole of crystal is known as lattice enthalpy. I will not go into detail, but in the note that you will find I have written in it. See, when the crystals form, we do not know how much energy it has released. So in that case, what do you do? We try to break it and we try to find out that how much amount of energy is being released. Because, say, take the example of sodium chloride crystal. In nature, when the earth was born, sodium chloride was not there, but sodium metal element was there and the chlorine element was there. So in that case, what has happened? It was in solid form. So gradually, sodium metal got converted into sodium atom. Okay. Chlorine is existing in, because chlorine gases, they exist in molecular form, not like metal. Then, in that case, gradually sodium has lost 1 electron and it has become sodium ion. Now the chlorine, I have to convert chlorine molecule to chlorine. So I have to break this bond. Then the chlorine has taken this electron given by sodium. It has become sodium chloride. As they are oppositely charged, they came together and formed that crystal. So, in that case, for formation of crystal, various types of energies are involved. From sodium metal to sodium atom, what is the enthalpy involved? Enthalpy of sublimation, because we have converted solid to vapor. From here to here, when it has become sodium ion, we have studied periodic table, we call it ionization enthalpy. So energy involved is enthalpy of sublimation, energy involved is ionization enthalpy. Here to here, what is involved? Bond dissociation enthalpy. From here to here, electron gain enthalpy. And after that, when they have come nearer to each other, they have come because of intermolecular forces of attraction. Ultimately, we have got this one. Okay, so lattice formation is multiple step. All right, so that I have written down, from there you read. It's not at all difficult. I've done the whole calculation also. Thermodynamics, did I send the note? I think I have sent you the note, na? Hello? Thermodynamics note I have sent, na? What happened? Are you not hearing?
Yes, sir.
Yes, so from there you read. So with this, we have come almost to the end of first law of thermodynamics. So in first law of thermodynamics, what we discuss? In first law of thermodynamics, we only discuss the movement of energy, flow of energy. Because of that, we call it thermodynamics. Flow of energy is taking place. Okay? And we found a relationship between work and the heat. It is work is directly related to the heat. All right? But what are the things thermodynamics does not tell us? See, thermodynamics did not tell us which will be the direction of the flow of heat. Okay? See, now all of us will know. Heat travels from hot body to cold body. But thermodynamics did not give us any information. So this is the major fault of thermodynamics. It has dealt everything with the heat, but nowhere they have mentioned where from the heat flows. Does it move from source to the sink? That is from hot body to cold body, or it flows from cold body to hot body. Second, thermodynamics did not tell us that why something happens spontaneously. When apple falls down from a tree, it directly falls on the ground. It doesn't go up. Water collected at the higher altitude comes down in the form of stream or river down the hill. Why does the evaporation of water takes place? And why most of the thing which is happening in nature is spontaneous? So thermodynamics could not tell us the spontaneity of a process. So that is the major fault of the thermodynamics. Okay, so for that, we must know why the some processes are found to be spontaneous. So before that, we should know the definition of spontaneity of a process. Definition of what is the meaning of spontaneous or spontaneity. Spontaneity is nothing but when the system is having an urge to do it. You don't have to tell. System wants it. See, many things which we like, nobody has to tell us to do it. We do it by ourselves. Sometimes we may be little lazy. In that case, some of your house member or may tell you why you are not doing it. Then after that, when you start, then you go on doing it. Okay? And why something does not occur? So we call them as non-spontaneous. Okay? Non-spontaneous means that when the system does not have an urge to do it. So we call them as non-spontaneous. Spontaneous process, I given you all the examples. If you put sugar in water, if you put salt in water, even if you don't stir it, it gradually goes into solution. Okay? If you have washed your cloth and kept it under the sun, you find gradually all the water which is there present in cloth, it goes out, it evaporates. It's a spontaneous process. All right? If you put a drop of ink in water, you find gradually the ink spreads into the entire body of the water and the water gets colored. Okay, these are all spontaneous processes. But you have never seen a river is climbing up the hill. Never. Okay, so these are called non-spontaneous process. All right. Now, we have to find out why. Okay, again, the spontaneous process can be classified into two categories. One, where no initiation is required. There is a third party is not involved. So when the water gets collected in a mountain, it comes down. No initiation is required. Water evaporation, no initiation is required. Keep an ice cube, take out the ice cube from a fridge and keep it in a plate outside. Gradually the ice gets melted into liquid water. No initiation is required. But in some cases, initiation is required. We know coal gets burns in an atmosphere of oxygen. So if you leave a coal outside, you have seen if you go to the Juwai side, both the side of the road, you'll find huge amount of coal is being stocked there for transportation. And we also know it is exposed to air. In that case, carbon should have reacted to the oxygen, but it never reacts. But if you take few pieces of coal, put it into fire, moment it becomes red hot, and on the red hot coal, if you put more coal, you'll find all the coals get burnt. So what does it mean? That it is a spontaneous process, but someone has to start it, initiate it. Just like that, when you take a matchstick and rub on the side of the matchbox, it burns. So you have initiated it. And once the fire has come out, then the process is spontaneous. Okay? So let us try to inspect why it is spontaneous. First of all, a process becomes spontaneous when it gives a more freedom. When freedom is more, then it is spontaneous. Suppose if the option is there, you got an option to go with your mother to her friend's house. And second option is that you want to go to your friend's house. So where do you want to go? Huh? Where you want
Friend's
to go?
house.
Why? Because in friend's house, you have more liberty. If you go to your mother's friend's house, you have to be very careful about the words that you use, the place you sit. Okay? And most of the people in their house is unknown to you. But when you go to a friend's house, suppose some more friend has come, then you find you are feeling more comfortable. You can exchange words with them, you can talk with them, you can play, and you can gossip, and so many stories are there. Why? Because in that case, you have more liberty. You have more randomness. You don't have to always be careful about your words, your attitude, the way you behave. No, nothing is there. No, you don't have any restrictions. So in this case, it becomes spontaneous. See, we find that there are some chemical reactions which liberate heat. Okay, because they are more stable in the form of product than in the case of reactants. All right. So in this case, we find most of the exothermic processes are spontaneous. Most of these exothermic processes are spontaneous. Okay. See, whenever you get angry, you shout. In that case, you don't see who are around you. In that case, with that extra heat that you have generated in your body, you immediately dissipate. This is a spontaneous process. But if you feel all processes spontaneous should be exothermic, then we are wrong. Why? We know conversion of liquid water to water vapor always require heat. So this is an endothermic process. But we find throughout the world, evaporation, when the evaporation of water takes place, nobody is heating the water. So this is an endothermic process. But still we find it is highly spontaneous. Highly spontaneous. Melting of ice requires heat. But when you have taken out this ice from there, you did not heat it. Why the ice is melted? Because when in ice, all the molecules of water are rigidly packed within the crystal lattice. They cannot move. When it gets converted into liquid water, molecules can move. But there is a restriction is there. It can move only within the liquid, which is occupying a small space in your plate. When the same water gets converted into water vapor, it is the whole universe to move. Anywhere it can go. So in that case, you'll find the process is more spontaneous. And that we call it as degree of randomness. It's a type of madness, is there, randomness. It can move anywhere. So this is one of the factors of spontaneity, which you measure and express the term as entropy. So higher the entropy, more spontaneous the process will be. And second condition that we are going to discuss, but anyway I still tell you, is called free energy. If the free energy of a process is negative, okay, we find the process is highly spontaneous. So that we are going to discuss. And from there, we'll try to formulate another law. This is called the second law of thermodynamics. That we'll discuss tomorrow. Okay? Good night.
Thank you, sir.
Thank you, sir.
Good
Night, sir.
night.
Good night.
Good night, sir.
Good night.